Hello everyone. Now let's move to sets and have some hands-on experience on set operations as well. Now look at this. We have certain amount of code over here and the results over here. So in the first statement, we have made a set using the set keyword which has A, B, C, D, E as its elements, and then we have another set containing D, E, F, G, H. So basically, the elements inside set are isolatedly stored. So when we say D, E, F, G, H, they are basically stored as different individual elements. Then we have printed using the print command set 1 and set 2. So you can see we have set 1 over here and set 2 over here. Then we have the differences. We have already seen how we can calculate the difference between two different sets using the subtraction operator. So when we say set 2 subtracted by set 1, it is going to remove all those elements of set 2 which are already present in set 1. So inside set 2 we have D, E, F, G, H, out of which D and E are common. So we are left off with A, B, C. So the result it gives is C, A, B. Next we have union. So when we say set 1 union set 2, it is going to give us all the elements present inside S1 and S2 collectively. So when we say union, look at this, we have E, G, B, F, D, C, A, B. So all the elements of set 1 and set 2. Then we have intersection over here. As you know, intersection provides us with all the common elements between two sets. So when we say set 1 intersection set 2, it is going to present us with all the common elements, and we have two common elements between set 1 and set 2, which are nothing but D and E. So over here we have E and D. Next we have the symmetric difference, and to understand symmetric difference, let's understand that. Now if we have set 1 and set 2, say S1, symmetric difference S2, it basically means S1 minus S2 union S2 minus S1. So this is the equivalent of S1 symmetric difference S2. So when we say S1 minus S2, what we mean is getting rid of all the elements of S2 present in S1. We are left off with ABC when we do that. So when we say S1 minus S2, we are left off with ABC union, and when we say S2 minus S1, we want to get rid of all the elements of S1 present inside S2. So we just have D and E, so we are left off with F, G, H. So we have F, G and H. So when we do the union of both of these elements, we are left off with A, B, C, F, G, H. So look at this, we have A, B, C, F, G, H. So these are the elements G, B, F, C, A, B, H, which are provided by the symmetric difference, and it does not necessarily gives us sorted elements. They can be shuffled and unordered. Then we have the superset. As you know, we use a greater than and less than symbol to check whether a particular set is a subset or a superset. So when we say set 1 greater than set 2, it probably means all the elements of set 2 are present in S1, which is not the case. We have D, E, F, G, H inside S2, set 2, and we don't have all the elements present inside set 1, so that this evolves to false. So we have false over here. Next we have set 1 less than set 2, which means that set 1 is the subset of set 2, which says that all the elements of set 1 are present in set 2, which is also not true. We have A, B, C, D, E present in set 1, and all these elements are not present in set 2, so we have false over here as well. Then we have to check whether an object is present in a set. We simply use the in keyword. So we simply say A in set 1. It will check whether A is an element which is present in set 1. So inside set 1 we do have A over here, so it evolves to a true. So that's how we perform operations with set. Okay, we have seen how we can perform various other operations in sets, and now we'll see how to use sets using those operations. So first of all, look at this, we have the commands over here and the results over here. So over here we have an operation which can be used to filter the duplicates. For instance, we have this list present over here containing 1, 2, 3, 4, 1, 2, 3, 5. Now as you can see, this list does contains repetitive elements, duplicate elements. So if you want to get rid of these duplicate elements, you can simply convert this inside into a set. So when we say L is equal to list set L, what it is going to do, it is going to get rid of all the duplicate elements. So when we say list after removing duplicates, look at this, we have all the elements without repetitives and without duplicates. Then we have isolate differences. So when we subtract two sets together, what it does is all the elements present in set 1 which are included in set 2 are discarded and only the different elements are presented. So over here we have 1, 3, 5, 7 in set 1 and then we have 1, 2, 4, 5, 6 in set 2. So in set 1, if you have a look, 1 and 5 are the elements which are present in the second set, 1 and 5. So we are only left off with 3 and 7. So look at this, it shows us the isolated differences which are 3 and 7. Next, if you can look over here, we have the first set containing A, B, C, D, E, F, G and the second set containing A, B, D, G, H, I, J. Now, if you can see in the first set, we have A, B, D and G already present inside set 2. So we have to isolate differences which are nothing but C, F and E. So you have F, C, E which are not present in the second set. So it has isolated the differences which are F, C, E over here. Next we have order neutral equality test. Now over here we have a list L1 containing 1, 3, 5, 2, 4 and list 2 containing 1, 2, 3, 4, 5. What we have to do is, while we say L1 is equal to L2, it is going to check whether both of these lists are equal or not. Although the elements are same, but if you are going to compare two lists together, it is going to evolve to a false. Look at this, it gives us a false. Why? Because despite the fact that they contain the same elements, the order of the elements are not equal. That is why L1 is not equal to L2 in case of list. Now when instead of list checking, when you do set checking, if you convert L1 and L2 into set, it is going to evolve to a true, because when you are dealing with set, it does not takes into account the order of the elements, it just takes into account the elements which are actually present inside the set. So when we say set L1 is equal to set L2, it evolves to a true, because despite the fact that the order is not equal, but yes, they do contain the same elements. Then we have dealing with large data sets. Now supposedly we have large data sets. We have one named as engineers containing Dave, Sam, Suzanne and Nina, and then we have other which contains Dave and Suzanne named as managers. Now when we want to apply intersection, that means we want common elements present in both of these sets, we can simply write engineers and managers, the intersection operator. We can use the intersection operator to get the common elements. So the common elements present inside engineers and managers are Dave and Suzanne. So we have Dave and Suzanne as the answer. Then we have union. When we want the union, we want all the elements of the set present together. We can simply use the union operator, which is this operator. And when we write engineers union managers, what it does is it gives us all the elements which are present in engineer set as well as the manager set without repeating them. So we have Sam, Suzanne, Nina and Dave, which are present in both engineers and managers collectively. Then we have a superset operation through which we can know whether the elements of one set are contained in the elements of another set. So when we say engineers is greater than managers, what it actually means, it means that all the elements present inside managers are present inside engineers, which means that engineers is a superset of managers. So which is the fact, so it evolves to a true. We can have a look over here that Dave and Suzanne are two elements which are present inside managers, and both of these elements are actually present in engineers as well. So engineers is the superset of managers, that is why it evolves to a true. So that's how we can perform various operations over sets. So let's get rid of this. Let's try to work with certain Boolean operators next, which is the last set of operations we'll be working upon in terms of data types. Okay, so these are the various commands and these are the results. So now as you know that Boolean types there are two Boolean types specifically which are true and false, and we can assign both of these Boolean types to a certain variable as well. Like in the first statement, when you look at this, we have A is equal to true and B is equal to false, which means that A and B are two Boolean data type variables containing true and false respectively. So when we say A and B, when we try to print A and B, it is going to perform the logical AND operation, which means that we've already seen that two Boolean variables, when operated by the AND operation, will evolve to a true only when both of them are true, which is not the fact. We have one true and one false, and that is why the answer will evolve to a false. Then next we have the OR operator. So when we have two Boolean variables and we have the OR operator applied over them, it is going to evolve to a false only in the case when both of them are false. Rest in every other case it is going to evolve to a true, at least if there is one true. So we have one true over here, that is why it is going to evolve to a true. Okay, now next we have the NOT operator. So the NOT operator, it does nothing but it just opposes the effect of the operand it is applied upon. So we have not A over here, and A contains true, that is why the NOT operator will negate its effect and turn it into a false. So we have a false over here, and then we have two other variables, C and D, C containing true and D containing false. And when we say print A and C or B and D, now what will happen, these logical operators will get applied over these variables bit by bit. So over here we have A and C or B and D. So we have A and C or B and D. Now when we work with both of these logical operands, the AND operand gets the first precedence over the OR operand. So let's replace them with their respective values. We have A as true and C as true again, or B as false and D as false again. So let's first of all get the AND operator working. Fine. So true and true will eventually evolve to a true. Or now let's work upon both of these AND operands. So false and false will definitely evolve to a false, and when you apply the OR operand over a true and a false, it is going to get as a true. So that's how it works. And look at this, we have a true over here. Now let's work with another. Fine. So next we have A and not B. So when we say A and not B, let's replace them with their respective values. We have a true and not false. First of all, we'll convert the negation operator. So we have true and not false will definitely evolve to a true, and when we have a true and a true, it is going to evolve to a true. Let's have a look what is the answer. So we have true over here as well. So that is how you work with Boolean logical operators. Now we have two values, num1 and num2, both of which are integers 4 and 3. Now how to operate bitwise operations? Now you can apply bitwise operations like bitwise AND, bitwise OR and bitwise XOR operations over a set of integers as well once you convert them into their binary equivalent. So we'll be converting both of these numbers into their binary equivalent and see what answer they give us. So let's try to do that. Fine. So the first operation we have is num1 and num2. Now we have num1 equal to 4 and we have num2 equal to 3. Fine. So when you convert a 4 into its binary equivalent, it becomes 1 0 0, and respectively when you convert 3 into its binary equivalent, it becomes 0 1 1. So when we are going to apply bitwise operators over them, okay, so let's begin over here. Now we have the first operator as the OR operator. We have num1 or num2. So when we say 1 or 0, it is going to evolve to a 1 obviously. Then we have 0 or 1, which is going to evolve to a 1 again, and then we have 0 or 1 again, it is going to evolve to a true, which gives us nothing but a 7. So let's look at the answer. The decimal equivalent of 111 becomes 7, so we get a 7. So let's look at the answer. So we have 7 over here, bitwise OR. Let's try to perform the bitwise AND over this. Let's get rid of this. So we have 1 and 0 evolving to a 0, because it evolves to a 1 only when we have a combination of 1 1. And then we have 0 and 1 again evolving to a 0, and 0 and 1 again evolving to a 0. So the decimal equivalent again is a 0. So we get a 0. Let's check the answer. So we have a 0 over here. Next we have bitwise XOR. Okay, so how do we perform the XOR operation? An XOR operation will evolve to a 1 when we have different opposite bits present, which means that a 1 and a 0 will evolve to a 1, but a 1 and a 1 will evolve to a 0, or a 0 and 0 will evolve to a 0, which means that if we are performing an XOR operation, opposite bits will evaluate to a 1 and same bits will evaluate to a false or a 0. So when we have XOR operation applied over 1 and 0, it is going to give us a 1. And similarly, when we apply it over 0 and 1, it is going to give us a 1. And similarly, over 0 and 1, it is going to give us a 1, which is nothing but a 7. So let's have a look whether it is a 7 or not. So we have the bitwise XOR as 7. So this is how you apply bitwise operations over binary numbers. Now, when we say print num1 is equal to num2, it is going to perform a equality check over first number and second number, which means that it is going to convert them into their binary equivalents and check every bit if they are equal or not, which is not the case. So it evaluates to a false. And then we say num1 is not equal to num2, which evaluates to a true. Why? Because both of them are different binary numbers. So that is how you perform Boolean operations over binary numbers and over bitwise